Hello, I'm Abdul Raheem, a ninepointer from IIT Bombay. In this video, we will be discussing a previous year question from ordinary differential equation of the year 2021. This is a question from a quiz that was conducted early on in the course, so it mainly covers some initial topics from ordinary differential equations. In this video, we will be discussing the seventh question. The dimension of the solution space of x square y double prime minus 4x y prime plus 6y equal to 0 defined on the interval minus 1 comma 1 is. So we have to find the dimension of the solution space of this differential equation. Okay, and the interval is given to be minus 1 to 1. Actually, we had a dimension theorem which said that dimension of a nth order differential equation should be n itself. So in that sense, the dimension of solution space of this second order differential equation should be 2 itself, right? If we blankly apply the dimensional theorem, yeah, I mean there is nothing more to do in this question. It should be just 2. But there were some conditions which had to be satisfied in order for us to actually apply that. What were the conditions? One was we had to convert the differential equation into standard form. Standard form means the coefficient of highest derivative should be just 1. So that means here I will have to divide this differential equation entirely by x square. So let me just do that. But before that, I'm just rewriting the differential equation. X square y double prime minus 4xy prime plus 6y equal to 0. So to convert to standard form, I'm just dividing by x square. So that will be y prime minus 4x divided by x square. That will be 4 by xy prime plus 6y by x square, that is equal to 0. And what was the other condition that was needed? In the interval we are considering, the coefficients of y prime and y should be continuous. And what is the interval we are given here? The interval we are given here is minus 1 comma 1, and in that interval is minus 4 by x and 6 by x square really continuous? If you think, no. At the point 0, minus 4 by x and 6 by square are not even defined, so they are not continuous at those points. So we can't blindly just apply the dimension theorem. So we have to do something in order to find. Okay. Still, in the interval minus 1 comma 0, I can say that dimension should be equal to 2. Similarly, in the interval 0 comma 1 also, I can say that dimension of null space is just 2 itself. Okay. Now it's just a matter of including that 0. Okay. So for that, first of all, let's just try to solve this differential equation. Okay. So just consider this part. This kind of differential equation has an important name, a different name, a special name it has. What is that special name? It's a Cauchy Euler equation. It's a Cauchy Euler differential equation. And what is the standard substitution to solve this differential equation? That is y is equal to x raised to m, right? Yeah. So let's just substitute that here in place of y. We will just substitute x raised to m. So x square into what will be y double prime? Y prime will be m x raised to m minus 1, and y double prime will be m into m minus 1 into x raised to m minus 2. So we will have m into m minus 1 into x raised to m minus 2. Then minus 4x y prime. What was y prime? M x raised to m minus 1 plus 6 x raised to m, that is equal to 0. Okay, now we can see that x raised to m is common in all the terms. Why? Because here there is an m minus 2 power, but along with that we have to multiply x square, so it will be converted into x raised to m. So that x raised to m is common. And what are the things left inside? M into m minus 1, which can be expanded as m square minus m, and we have a minus 4m here because x and x raised to m minus 1 together as x raised to m just come out. Okay, and we have a plus 6 here, that is equal to 0. That means m square minus 5m plus 6 equal to 0. Let's just m square minus 5m plus 6 is equal to 0. We can factorize this into m minus 2 into m minus 3 equal to 0, which gives the possible values of m are 2 and 3, which gives the given Cauchy Euler equation has solutions as x square and x cube. Okay, so in the interval minus 1 comma 0, this can be a solution, right? So in that interval, what will be the solution look like? The general solution will look like ax square plus bx cube when the value of x is between 0 and minus 1. Okay, this is the form of the solution. And similarly, in the interval 0 comma 1 also same thing would work, but we will have cx square plus dx cube. Okay, similar thing would work, but the only issue is with the point 0. Okay, as of now, we don't have any solution for the differential equation at x equal to 0. But on the subintervals, since we have these differential equations, these solutions, let's just try to extend them in some way. Can we really extend them? Like, what should be this function's limit value as x tends to 0? That should be 0. And what should be the limit value if we put x tends to 0 on this side from the right side? That is also 0. So it's okay, we can try putting this as equal to 0 on both sides, because if we define the function, if we define the y function to be equal to 0 at x equal to 0, that is, if we substitute y of 0 equal to 0, these definitions already holds and the function is continuous. Okay, now we just need it to be twice differentiable in order to be a solution for the entire differential equation. Okay, now let's just check if this is actually, can we make it in such a way that this is twice differentiable at the point 0, at x less than 1 and at x less than 0 and at x greater than 0. It's just that it's a continuous differentiable nice function, it's just a polynomial function. But now at 0 we need this to be twice differentiable. Okay, so let me just calculate the first derivative blankly. Okay, I'm not saying that it already exists, but if it exists, what should be that? I'm just calculating. It will be 2ax plus 3bx square, and similarly here we will have 2cx plus 3dx square. Okay, there are interval x belonging to -1 to 0, and here we have x belonging to close 0 to 1. Okay, now is it actually differentiable at 0? As x tends to 0, this term goes to 0, right? Similarly, this term also goes to 0. That means this function is differentiable at x equal to 0. Now let's try the second derivative. What will be the second derivative? It will be 2a plus 6bx square, and here we will have 2c plus 6bx and 6dx. Okay, and we will have the interval conditions here. Okay, now if we substitute x on both sides, we will require the condition 2a equal to 2c. Why? Only this will be twice differentiable at the point x equal to 0. Okay, that means a should be equal to 0. Okay, so we had found the solution for the interval less than 0 and greater than 0, and extended that by putting 0 at that point, and we found if a and c are equal, in that case it can be twice differentiable and it can satisfy the differential equation. So in the entire interval -1 comma 1, in this entire interval we can define y of x is equal to what? Ax square plus bx cube, when the value of x is between -1 and 0, and similarly instead of c I will substitute a only. Okay, ax square plus some dx cube at the point at the interval 0 comma 1. Okay, this can be closed here. So we have found a solution. Okay, now what is its dimension? What is the dimension of this solution? Actually, you can directly just say that the dimension should be equal to 3. Why? Because there are 3 distinct degrees of freedom. A is a degree of freedom, B provides another degree of freedom, and D provides a degree of freedom. So you can intuitively say that the dimension should be equal to 3. In fact, you can find a basis of this solution space also. How? Just put A equal to 1 and B equal to D equal to 0. Okay, in that case, what will be the y of x? Y of x will be simply x square in the entire interval. Okay, so we got one solution as x square. Similarly, just put a equal to 0, b equal to d equal to 1. What will be the solution? Y of x is equal to, we will have x cube in the positive region and x cube in the negative region. So in general, we have x cube as the function. Okay, now let's substitute a equal to 0 and b equal to 1 and d equal to -1. Trying to find 3 functions from this general solution such that they form a basis, and that means they are linearly independent. We need to find such functions in order to be sure that this has the dimension equal to 3. Okay, if we substitute this a equal to 0, b equal to 1 and d equal to -1, we will have x cube on the negative region. Sorry, we will substitute -1 here and +1 here. Even the other one works, but this will look a little more better. Okay, I will substitute b equal to -1. Okay, so I will have in the negative region minus x cube, and in the positive region I will have x cube. Okay, so in the negative region I have minus x cube, in the positive region I have x cube. So what is this function actually? This is actually negative on the left side and positive on the right side. Which is that function? That is actually modulus function. So this is actually equal to modulus of x cube. This can be written as x square mod x, because the x square is always positive, right? So we can just take that out. Now it's very easy for you to check that these things are indeed linearly independent, because you can just directly claim that they are not scalar multiples of each other, so they should be bases, they should be linearly independent, and this a basis. So x square x cube x square mod x forms a basis, and we have the dimension 3. Even this degrees of freedom technique is enough, but just to give a little more rigorous proof, I have found a explicit basis for the solution space. Okay, I hope that this was clear. If you had any doubts, you are expected to write them in the comments. We will be responding there. And thanks for watching the video. Stay tuned to the channel. We will be coming with the remaining questions and even end semester questions on upcoming videos. So stay tuned to the channel. Bye.